We're happy to have you here, and we're very happy to have Guy with us, telling us all about the theater again.
Okay, so let's have a little recap. So we have this picture of the birth of the universe that gives us a theory of structure formation. We think that the universe underwent this accelerated expansion, cosmic inflation. Universe expands very, very quickly. And then there are small quantum fluctuations that get amplified by the expansion of the universe, and they leave an imprint in the form of primordial seeds, primordial correlation functions. So to explain everything we see today in data from galaxy clustering and the microwave background, all we really need is a non-trivial two-point function. So again, if we draw the timeline of the universe, we have here the surface at the hot Big Bang, then like the putative time equals 0, then we need these non-trivial correlations. But they can be explained essentially by free field theory, just a Gaussian random field, a very light scalar of mass much smaller than the intrinsic energy scale. During inflation, Hubble, we worked in the approximation that m is 0, good approximation. And if we quantize the free field in this geometry, we get the scaling variance. So the scalar field two-point function in momentum space, k minus k. Remember that remember this little bit of notation. If I put a prime, I strip out the momentum conserving delta function. And if it's canonical, this field, then it has units, and the energy scale that controls its two-point function is the Hubble scale, and then at late times, this is its two-point function. Something survives to arbitrarily late times. So the curvature perturbation is pretty much the same two-point function. The only difference is that it's in some units, and so there's this 1 over 2k cubed here. It comes from scaling variance, but it's a dimensionless quantity, so what appears here is h divided by m Planck root epsilon squared, okay? So we had this little arrow of the energy scales, where here's the Planck scale, here be dragons, we have no clue. There's this other scale that because we don't know epsilon, we don't know how far it is from the Planck scale. And then there's the Hubble scale where the experiment happens during inflation. Then we are somewhere down here, okay? And, right. So in fact, I mean, down here there's another interesting scale, which is epsilon h, which if you remember, these ratios of scales, they control different physics. So this is what we see. So essentially, to explain the universe, this is what we need. So this is a very important formula. Many people contributed significantly to obtain this very simple formula. This formula explains all structure that we see in the universe. And the other general prediction of inflation is that there are gravitational waves, and their two-point function is controlled by different ratio of scales. Maybe there's a factor of 8 here. Okay, I don't care, I don't remember. This is h over, so for every polarization mode of the graviton, you need to correlate the same polarizations, and you get this ratio of scales. Okay, this we haven't seen, and therefore, what we have seen is controlled by this ratio of scales. So this is controlled by the scalar two-point function. And this ratio of scales here, if you remember, controls the scale dependence, and S minus 1. Unfortunately, it's not epsilon alone, because this would give us a measurement of this energy scale, because of course we know what the Planck scale is. But there are other scales here. In slow roll inflation, there's also eta times h, right? The second slow roll parameter. So an S minus 1 involves an admixture of these scales. It would be very nice to know epsilon, because then we'll know the Hubble during inflation. Okay. So that's where we stand. And then we started discussing non-Gaussianity. Non-Gaussianity. So we had a little bit of a cartoon picture of how that works in the colloquium. And non-Gaussianity is about interactions. So for example, you can have some interesting three-point function, and there are a few scenarios for what it could be. It could be just self-interaction. And we argued that this peaks around the equilateral limits, okay? Or it could be due to some interaction with a messenger. Okay? So I want to give you some flavor today of how you compute these correlation functions, because they are interesting functions, and there are different methods to compute them. And this, I promised, will be responsible, okay? This is by now cookie cutter textbook, and then we'll see, depending on how energetic you are for the second lecture, I will go wild or I will continue following the textbook route. So the idea, there was a question by Rogério Rosenfeld in the colloquium, if you remember. Oh, first of all, does this diagram bother you? If you're a particle physicist, you should be somewhat bothered by it. Does this diagram bother you? Does this diagram bother you? Yes, it's a yes or no question. Yes or no? No? All good? I don't care. It should bother you. Why? This is a little bit funny, no? Usually things decay because there's a reaction, right? Things don't spontaneously become other particles. So actually, what prevents this from happening? Okay, the technical term is linear mixing. Why is there no linear mixing in particle physics? Yes. What's it called? That's the right answer. What's it called? Huh? No. Not energy. Not energy. It's an anagram of this thing here. What is it? Boosts. Yes. It's boost symmetry. It's it's forbidden. You can go home and you can try. You can try writing linear mixing Lagrangian, and then you see you can do a filter definition that rediagonalizes the basis, and then you have quadratic terms in the Lagrangian. This is forbidden because of boosts. So in cosmology, in de Sitter space, this is forbidden. So if we go to de Sitter, this diagram is not there. But what you can do is the following. You can do this diagram here, and with the same messenger. Let's see, I was using blue. Okay, So this is the diagram that you would compute in the Sitter space, a 4-point function. But then what you do is you deform it a little bit. What you do is you take one of the legs, you take this momentum here, and you make it very soft, this K4. So this is 1, 2, 3, 4, and you send K4 to 0. So when you do that, this leg has very long wavelength. It redshifts away very slowly, and then what it does is it mimics a non-de Sitter background. So this is roughly this diagram that we were drawing. But the background geometry is different. So the background geometry is ds, while here the background geometry is low roll inflation. Okay? So that's the idea. So if I put the approximate here, I mean that it's almost literally the same, but you pay a price. There's a coefficient that suppresses this signal. Do you see why this will be suppressed? Yeah. Why? Well, because you want it to be a background wave that very slowly redshifts, and these three other hard momenta feel a modulated geometry. So you remember, slow roll inflation is a scale factor that is approximately e to the ht, but not quite. But importantly, it's a space independent. So when you send K4 to 0, you give this physical wavelength to be much bigger than the wavelengths of these other guys, so they feel this as a background wave. Okay? So it mimics, so in the end, it adds a little bit of stress energy, such a way that it mimics this scale factor here. Okay, so that, yeah. Now, why do you pay a price? This is suppressed. Do you see why? You need to, I mean, the formulas are very beautiful. I can write lots of formulas, okay? Very, very cool formulas, but I want you to get some intuition. So this will be suppressed. This limit will be suppressed. Do you see why? Just think of the dumbest picture of inflation. When things happen, they tend to be stretched by the same amount. Don't you create a tension when you write a diagram like this? That's right. So if you want to create this big hierarchy, you need to pay a price. And this price is essentially the slow roll factor, epsilon. Okay? So this epsilon we know is very small, and the suppression comes precisely from this tension between taking the soft limit on this leg and keeping this momentum hard. Something survives, but the diagram is suppressed. Nonetheless, the shape, the function, so this is very small. It tends to make the whole thing very small, but the K dependence is very useful. You can bypass this using effective field theory. So it's a useful crutch. So for this reason, this diagram is very interesting. It's the thing that you would try to search for data immediately, but we're going to take a step back and we're going to study this example here, the 4-point function, when you exchange a scalar. Okay, so we're going to exchange a massive field of spin equals 0. And the other thing I'm going to do is we are interested in the case when these yellow fields are massless, because that's the thing that survives to late times. But I'm going to do another simplification. Instead of m squared equals 0, I'm going to choose m squared equals 2, which is the conformally coupled scalar. And this is for simplicity. The formulas just look simpler. Of course, in this case, then the signal redshifts away. So in this case, for conformally coupled scalars, the 4-point function, phi 4, red shifts away. As eta goes to 0 at late times, it goes like eta to the 4. So it's going to 0 times some interesting function of the momenta. Okay, 1. And I would like to tell you a bit how we compute this function. And the claim is that if I understand this function, then by some slick group theory that comes from the fact that you have the Sitter invariance, you can obtain the thing you care about, n squared equals 0. It's essentially some derivatives applied to this case. So this case is easier to understand, okay, technically. And this group theory is so powerful that if you do scalar exchange, you can get spinning exchange also. So that's kind of neat. So let me just draw a little diagram here. So this is our seed. I'm gonna study. Maybe I should change the color. So this is m squared equals to 2h squared. And this is m0. And from here, we can do kinematic moves. We apply some operators that depend on the momenta. And then you can obtain, for example, this case here when you exchange m0. From here, you can apply other operators, and you can obtain spin exchange. So you can make this particle spin, m non-zero, j non-zero. You can even do crazier stuff. You can shift the mass. The other interesting thing is you can spin up. So for example, we know that the graviton is there. We haven't, I'm running out of color. We haven't seen the graviton, but we know that it has a 2-point function, this guy here. So one thing you could imagine doing is you could imagine studying graviton correlators like this and stuff like that, for example. You can even spin up. So group theory is the gift that keeps on giving in the Sitter space. I guess you learned something about that from Dio, from the representation theory. So there are interesting operators, they're bilinears, they're called weight shifting operators, that allow you to massage this 4-point function and land you on different dynamical processes. So it's not that for every diagram you need to go back to the drawing board and recalculate it. If you compute this, you compute all of these other examples. So it's kind of cool. Okay? Any questions about this? So if the punchline is, if we understand this diagram, massive exchange of conformally coupled scalars, then we understand many things, and we can go back to what's physically the most interesting for observations, okay? And we can put one leg on the background, and so this will take us to the thing that I was drawing before on the board. So this is soft limit. Okay. So let's see how one computes that. Well, first of all, maybe, I guess you've seen what the answer looks like if you were paying attention at the colloquium. So remember that the answer for this diagram was if you start with all the legs at equal distance from each other in a square shape. So this had sort of featureless. There was a lot of power, but somewhat featureless signal. And then as you squeeze the momenta, then some interesting things happen. So let's see if I... So let's take momentum ratio. And this is like 5 to the 4 multiplied by some factor that just enhances the behavior in the squeeze limit. So, for example, if you started here with the equilateral-like configuration, so all these 4 points are equidistant from each other, and then as you go down the line here, you end up on some squeezed configuration like this. So let's say you squash along the diagonal, and I'm also squashing on the left, such a way that these momenta are of similar order of magnitude, and these ones remain bigger. Okay? So what happens is that the plot ends up looking like this. So you have some boring, featureless result that is, you can approximate the answer by just hard contact interactions. So, which is the usual intuition, right? And when, okay, let me contrast with particle physics in a second. And then as you squeeze, you'll see the messenger propagating over time, but with this feature that I was making a huge deal about in the colloquium, that it comes from the fact that this particle is going to traverse many Hubble volumes. Okay, so this is what the answer should look like. It's kind of an interesting function. It's some special function called the Campé de Fourier function. Right. So let's contrast with particle physics. So in particle physics, you would make a plot of, for this type of diagram, it would just be some S channel. 1, 2. So this is particle physics. Well, we know what the answer is. The answer for the diagram is just G squared over S minus M squared, right? So that's it. So we're just looking for the analog of this formula for the cosmological correlator, where S is the Mandelstam invariant, is P1 mu plus P2 mu squared, is the center of mass energy. So if I plot S here, and I plot the scattering amplitude here, then I see that at M squared, it has a big feature. I mean, and then off it goes. Okay, then it decays. So this part of the plot is something that you would fit with effective field theory, just with hard contact interactions, which is what you would do here. Okay? Here there's EFT. And then around this, when you see the spike, then you discover new particle. So then here, there is particle production. Okay? So then you discover the spectroscopic data of the particle. You discover its mass. So how do you find out the spin of the particle? If you're a particle physicist, what do you do? You guys need to take particle physics. Less ideas CFT. So what do you do? How does the LHC discover spin of particles? You know, the Higgs, when it was discovered, people didn't know if it was spin 0 or spin 2. I mean, everyone knew it was spin 2, but I mean, it could have been spin. So everyone knew it was spin 0, but it could have been spin 2. So how do you tell? Echo. So precisely. So you go close to the pole and then you change the scattering angle. So that's why the LHC has detectors all over, like in a cylinder, because the way that the scattering results are distributed the angular distribution. So if I had spin, I would have Legendre polynomial here. So this comes from group theory that depends on spin and depends on cosine theta, the angle between the, so if you boost to the center of mass frame, you'd have 1, 2, have the collision, then 3 and 4. I mean, we usually work in conventions where everything is incoming, use crossing, and then you talk about negative energies. And then this cosine theta is this theta here, okay? So there's some Legendre polynomial. And importantly for us, Pj of cosine theta goes like t to the j, okay? So there are two Mandelstam invariants at 4 points, S and T. And in the S channel, you get a pole, and the residue at the pole is a polynomial that goes like t to the j. So that's how you extract spectroscopic data from a collision, okay? So we would like to understand how the same story works here. So this part is, by the way, let me just to finish the thought here. Once you are past the particle production threshold, then here you upgrade your EFT. So then you continue marching on. This is the history of particle physics, but then you have an EFT 2, okay? So here's the EFT of Fermi theory, before you discover the W boson. Then you see a big spike. Some people collect Nobel Prizes. Then you continue marching with an EFT with new states. Okay. So now, of course, the physics, this particle is very light compared to the energies that you're probing. So you better incorporate it in the EFT. Okay. So here, because the experiment is done at a fixed energy, the way you see particles is by going to the soft limit, by giving them enough time to propagate. But the signal is becoming weaker. Okay? So that's the difference. And so here's where you see particle production. If you wanted to do something like the EFT2 part of this plot, it's not entirely clear how to proceed. I think you would probably need to go back, incorporate the particle that you detected, compute the full shape, subtract it off, and see if there's some leftover signal, because you can't continue cranking up energy, searching for new particles. What happens is that all particles, they are produced in the soft limit, but they have different decay rates, depending on how light or heavy they are, okay? So I'll comment on that. So just to contrast that, these parts of the plot are very much the same for particle physics compared to cosmology, but how you incorporate the new physics and continue marching on is a little bit different in this case. Okay. So how do you compute this? There are 3 ways. So there are 3 ways, and actually there, my friends Bauman and Joyce have some nice lecture notes. They are not on the archive, they are work in progress, but they're on GitHub, so these people are very modern. So it's GitHub of Daniel Bauman. So if you put Daniel Bauman on GitHub, then you'll find he wrote a nice textbook in cosmology, and he has also some link to their lecture notes. It's 150 pages of lecture notes, and there you can learn everything about how to compute these cosmological correlators from various viewpoints. So there are 3 main techniques to computing them. One is using what's called in-in or Schwinger-Keldysh formalism. So this computes the actual observable, okay? The expectation value of the fields at the end of inflation. So this is like going straight for the final observable. Then there is something else that you can do, which is an auxiliary object that turns out to have lots of nice properties, and it resonates a lot with what we do in holography. That is called the wave function of the universe. Okay. So this is the object, and then the method to compute it is using on-shell actions. Okay. So this is also famously due to Harton-Hawking. But there's a version of their story that works for quantum field theory in a rigid background, maybe with small gravitational fluctuations. And then the last way of doing it is more recent, is using bootstrap methods. So these compute both in and wave function. And essentially the main piece of technology is by using differential equations. Differential equations. And these differential equations follow from two main ingredients. One are the symmetries of the problem, and the other are the singularities. Okay? So once you know the symmetries and the... So what's the idea of bootstrap? Is that maybe you're not infinitely powerful for a given theory. You can't compute all possible observables of a given theory. But maybe if you're less ambitious and you focus on a few observables, then you can say very general things about these few observables, okay? And then you can try to bootstrap them. So these methods are all powerful and they apply to any given theory. They give you a recipe in principle to compute everything you could imagine from that theory. But although they are in principle computable in practice, to actually get an answer, they run out of steam relatively quickly. And here the idea is that, well, maybe you can change the perspective, think about new general principles to try to bootstrap the observable, and it turns out to be practically a very useful way of computing them, maybe more efficient than the other routes. So in the ideal world, if you were very energetic, I would take maybe 10 more hours of lectures and explain all of that to you. But what I would do is I'll just try to give a very quick overview of these methods and explain where we land, okay, for each one of them. So, are there any questions? Yeah.
I'm just curious about the wave function of the universe. I assume that it must come from a path integral, right?
Yes.
So like, for a given wave function, one can obtain probabilities, but when one has like a wave function of the universe, to me it's weird to interpret quantum probabilities. So like, how is the interpretation of this object, or are you going to discuss this in the following minutes? How is it?
Yeah, not really. I mean, it's related, I think I mentioned this in the lectures, that the working assumption of cosmology is that each patch of the universe is a different realization of the same underlying state.
Okay, okay.
So the idea is that ensemble average over the universe is some average, you know, what's the word? Frequentist averaging of the same underlying wave function. If you, yeah, I think if you don't use this assumption, then it's difficult to think about the wave function of the whole universe, because there's only one universe, and I mean, yeah.
So the idea, we have a wave function, one can compute probabilities, but one interprets these probabilities as predictions for patches of the universe.
That's right.
Something like that. Okay, okay.
Yeah.
It makes sense. Thank you.
That's right. Okay. Anything else? So these two methods, they do slightly different things, but in the end, when you compute the, in practice, at least for these simple things that we're discussing, tree-level correlators, low points, they have similar rules. You have some propagators, like Feynman diagrams, standard QFT type of propagators. The details differ for one case versus the other, but roughly very similar. So let me describe the idea. So in, so let's start with in, one. So remember that the quintessential property of QFT in curved space is the spontaneous production of particles from the vacuum. So the usual assumption of QFT in particle physics, that the out state is just a rephasing of the in state, is just false. So then what you should do instead is you control the initial state, and then you time evolve the initial state with the Hamiltonian. So in order to do that in practice, then Schwinger and Keldysh, they essentially implemented the interaction picture, but for the bra and for the cat. So in the usual Feynman, like in-out picture, you have time evolution, and then you insert some operators, okay? O of T1, O of T2, and then you time order, and then you evolve things with the Hamiltonian forward in time. So then you compute time, you compute the typical thing you compute are Green's functions, right? So there's a out time ordered O T1 of T2 in etc. Okay? So you have a single, so in order to do that, what you do is you go to the vacuum of the free theory and you do the time ordering of this Dyson operator, right? E to the minus I integral from minus infinity to infinity of the interaction Hamiltonian, H int, of T prime times O of T1, O of T2. And to make sense of this, we introduce the usual machinery, Feynman diagrams, and propagators, and It's essentially about this object, well, divided by out in, divided by 0, time order, e to the minus I integral H int. And this, guys, is the reason why when I compute diagrams, I throw away bubbles, right? So if I have a diagram like this, I don't care about the bubbles. They're disconnected like this, right? So this is accounted for by this denominator, right? So this is the usual story, usual in-out. In, instead, you contrast in. So for us, we are interested in the expectation value in some state of some operators, like say 5 to the 4, evaluated at some time t that is towards the end of inflation, for example, t going to infinity, cosmic time going to infinity, or eta going to 0, right? But then to prepare the vacuum of the interaction theory, we need to time evolve it using the interaction Hamiltonian. That's standard, right? So that's how we do it in QFT textbooks. But now the difference is that you have to time evolve to generate the cat and to generate the bra. So therefore, the time contour gets doubled. So this is what you end up doing. You evolve, you do time evolution. Let me call this T star. Minus infinity to T star. H interaction, dt prime. And then you do the dagger of this operator, which is T bar e to the plus I integral H interaction of T prime dt prime. T star. And here, okay, this is really for the aficionados, but there's a little bit of a fine print of how to do the I epsilon prescription. So the I epsilon prescription is different for each branch of the contour. So, I mean, strictly speaking, if you thought of this as going, if this is the real axis, you go off into the complex plane in one direction here, and you go off into the complex plane in another direction here. And mistakes have been made in the past because people were not taking this very seriously. So this is important, okay? So the let's say I put minus infinity minus here. So here, because the complex conjugate, there will be minus infinity plus. So you need to adjust the I epsilon also. Okay? So that's the difference. And then you insert your operators, the O's, you insert at the top here. Okay? So this would be, sorry, the picture got too busy. So this you insert phi hat to the fourth. Notice that because this propagates you forward in time and this propagates you backwards in time, I mean, of course, after I insert the operators, if I continue moving forward, the backwards motion just cancels it. So after I insert the last operator, there's no point in continuing moving forwards and backwards. Another way of saying it is that there's no denominator, right? Because you're doing the inner product of the state with itself. So there's no analog of this guy here. Because this guy is just the time evolution from minus to plus infinity. Now these things cancel. Another way of saying is that there's no in partition function, right? Because the partition function is just the time evolution operator forward and backwards. Okay, so this is in. In practice, what happens is that the propagators change because now you have propagators that move you. So for example, if I have a propagator that propagates an interaction point from time t1 to time t2, then nothing changes compared to Feynman. You just use a time-ordered propagator. So this is identical. But you can have propagators that move you from here to here. This is anti-time ordered propagator. Or you can have propagators that move you from here to here. And this all, of course, there's no time ordering to pick because obviously this is always before that. So that's a Whiteman function. You see what I mean? Usually when there's time order, I mean, here you have to decide like which one goes first, which one goes after. Here it's anti, but when you connect these two different branches, the time ordering is fixed. So strictly speaking, there are two different types of propagator. Time ordered and its complex conjugate and Whiteman-like propagators, okay? So that's, we like to say that we double the number of fields. So you double the number of fields, you double the number of propagators. So, I mean, you double the number of time contours. So the work is a little bit more complicated, but not much more complicated. So just to give you a flavor of what happens for, we're going to do some actual computation, but not in that example. It's to gain some intuition. But just to give you an idea. So if I have a 3-point function, okay, so then I would have a propagator. So this is the moment in which I do the measurement. So the time contour runs like this. even though this is the measurement. So this moves me forward in time, and this moves me, the upper part moves me backwards in time. I'm just unfolding the time contour. I open up this time contour, okay? And I have different type of propagator in the upper part of the board. So here there will be two diagrams. There will be this diagram with the propagator that moves me in this direction, plus another diagram with different propagator coming from this part here. Okay? Is it clear? If you stare at the picture there, you see that if I insert an interaction vertex on either side of the contour, this is the interaction vertex, and then I have to use different type of propagator. Okay? Very good. So what happens at 4 points when I have an exchange, like the diagram that we are interested in? At 4 points, you're going to have this. Now there are propagators that send you from this point to this point. They're Weitman functions, right? Because the time ordering is fixed. This is the Feynman propagator. It's time ordered. So if there's T1, T2, there's going to be different terms and so on. But the time ordered propagator accounts for that. And these are Weitman functions. So these were all Weitman functions, but with specific time orderings. You know, this is to the past of these, and this is to the future of these. Now here, the two types of propagators make an appearance. Do you want me to color code this, or is it clear? Yes, what? Yes, it's clear, or yes, color code?
I'm hearing yes, color code, please.
Ah, okay, yes, color code. Okay. So here it's Weitman. And maybe let me give arrow of time. And here it's Weitman with arrow of time like this. Okay? Here, Weitman. Here it's Feynman. Okay, so maybe. So now there will be different diagrams. So what happens? I can now put the one vertex at a time in the upper part. So I can have a diagram that looks like this. I can have diagram. And now here, what do you think it is? Do you think it's Feynman, anti-Feynman, or Weitman that connects? Huh? Weitman. The time ordering is fixed, right? And likewise the opposite, so there will be this guy here. And then there will be the anti-Feynman. Okay? Oops. Okay, so these are the 4. So you need to add these 4 diagrams. Okay. So this is the story. So then if we had our 10 hours, I would write all the propagators and and do some computation for you. That's in. So we're done with this. Let's move on to wave function.
Sorry, one question before we move on. In the comment you made about the denominator there, if I try to compute omega inner product with omega, I just get a plain 1. Right?
Yeah.
That is another way of saying that I could add the denominator, but it's just the inner product.
It's just 1.
Okay, thank you very much.
In outs, it would have been 0, the time evolution operator from -infinity to infinity, 0. But in, you have 0, U dagger,
Exactly.
0. Yeah,
Thank you very much.
Very good. So now let's okay. So we're done with in. Let's do wave function now. So wave function, that's 2. For the wave function, what you're interested in is different type of question. So the wave function of the universe, it depends. It's a bit funny. It's like a Schrödinger picture QFT. So we compute at a given time, t star, or t going to plus infinity. We compute the amplitude for the universe to have a specific field configuration, phi of x. So this, we were computing the expectation value of the field operator as a hat, as a function of position, where you insert the operators at equal time. While here, we compute for a given C number configuration. So I have some time slice, t going to plus infinity. I compute the amplitude for the universe in the vacuum state. So this is, of course, the wave function for a state, but we always assume that we are in the vacuum. And it's interesting because of the usual particle production story. Now there's going to be some C number field configuration, phi of x. Okay? So, how do we compute that? Okay, so we write some formula that is a path integral. Of course, nobody knows how to do it, but you write, to look fancy, you write path integral. You integrate over all fields. Going to be some phi of tx. You're going to integrate now, or maybe I should change notation. You're going to integrate over all 4-dimensional phi's. Okay? And now the boundary conditions of the path integral are different. So you want, at minus infinity, you want regularity. And we're going to discuss what that means in a second. And you want, at plus infinity, you want the field configuration. So you integrate over 4-dimensional fields off shell, any field configuration you want, as long as the field gives some regular contribution to the action. And that selects the state. And then at late times, the value of phi as t goes to infinity, and x equals phi of x. Okay, so this is where the data comes in. And then, of course, e to the I action. Okay, so that's it. So this is the path integral. And because we are weak, we approximate this by some semi-classical approximation. Okay? Compute this as e to the I, the action of some classical saddle. Now, if I write something like this, something that should worry you immediately is that this wave function is not interesting. Is there something that you'd be suspicious about this formula? If you say classical solution, okay, there's some nonlinear field theory, phi cube theory. So here's phi cube theory, right, that we're doing, because there are cubic vertices. So let's say that the Lagrangian of the theory is this. Then we like those conformally coupled scalars, but okay, for now we keep the mass a free parameter, and then we add phi cubed. Okay. then, I mean, it's the equations of motion are some nonlinear equations, phi squared and so on. Then you find some solution. Regularity, maybe you don't want the solution to blow up at early times. And then you plug it in here and you reach, naively, you reach a sad conclusion. What's the sad conclusion? It's wrong, okay? It's good, everything will work, but there's some knee-jerk reaction that should give you pause. So what is it? Yes, DI. Because it, does it mean, you know, to compute probabilities we use what our friend Max Born told us. You do compute this, psi squared. But then psi squared is 1. So this is wrong. So what's the way out? Louder? That's right. So the saddle is complex. So even though things are kind of similar and the diagrammatics are ultimately the same as here, I mean, they're very much similar, then the point is that the solutions in which you evaluate this action, they are complex valued, okay? So let me describe this example for the massless scalar in DS. So here we're just talking, I mean, this is of course fancy, non-Gaussianities and so on. But let me take a step back and just describe the free Gaussian field for which we already did canonical quantization, okay? Just to contrast, so I'm gonna do in for the Gaussian free field, so there's no interaction Hamiltonian. So the analog of in would be canonical quantization, and let's see how the wave function works. Okay, so this is a very illustrative, so forget interactions. Let's step back to free fields. So the Lagrangian is and let's discuss m equals 0 in DS form. Okay? So, in canonical quantization is what we already discussed many times. You write phi because integral over all the Fourier modes, d3k of ak phi classical plus Hermitian conjugate, where phi classical is given by this, right? H over this, if you work on the seater, you know by heart, 1 plus ik eta e to the minus ik eta. Okay, very good. And then from here, this is the field operator, then the 2-point function. When you strip out the delta function at late times, as eta goes to 0, is what we just discussed in the recap. H squared over 2k cubed. Okay? Very easy. So now let's see how the wave function gets the same result, because it's a bit different. And when you're confused, you keep taking step backs. Keep taking step backs. Just be careful not to fall in the abyss as you take steps back. So let's do the wave function of the simple harmonic oscillator, okay? The simplest, can't get any simpler than that. So The Lagrangian is just this. Okay. So, equation of motion. Phi double dot plus omega square phi classical 0. Phi classical is a alpha e to the minus I omega t plus beta e to the plus I omega t. And we had some story about how to do canonical quantization. We should pick e to the minus I omega t, and we normalize the coefficient, and yada, 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 okay? So now, regularity. So regularity. Really means that as time goes to minus infinity with the proper I epsilon prescription, with proper I epsilon, the solution goes to 0. Okay? And, well, so this actually, if you do the proper I epsilon, it turns out that the right solution is you want phi classical to go to e to the plus I omega t. Okay? I mean, this plus or minus maybe is a little bit conventional, but the important thing is that it's single frequency, so that when you go into the complex time domain, this omega, if it's positive, damps the classical solution. So far so good. This looks very similar to what you would do in canonical quantization, but here you're solving different problems. So here, this is harmonic oscillator, so there's only time, okay? So there's regularity as t goes to minus infinity. And then at your point of observation, where you compute the wave function, let's say t star equals to 0, for example, you want the wave function now has argument t star, and the data is phi, the value of the field at t star. Maybe phi is doing too many duties here. Let me call it f. So this is just a real number. Okay, it's the argument of the wave function. So I want the classical solution to have value f at t star equals 0. Gotcha? So what's the solution? Phi classical. That's it. There's no Wronskian root 2 omega and so on. Okay? Now you plug this into the action. It's quadratic, you integrate by parts, it solves the equation of motion. It's the boundary term when you integrate by parts that gives the wave function. And then when you do that, then you get, well, nobody's going to be shocked by my analytic power. You're going to get this, okay? So that's the answer. So oops, I think I messed up. This is the answer, I think. Yeah. So, okay. Very good. So from here, you get the 2-point function by using Born's rule. So the 2-point function, you take mod squared, you put f1, f2. Okay, but here it's so boring, there's no separation, that there's nothing interesting. So let's go back now to the case of ds, of the massless field in ds. I didn't want to, okay, I'll erase this. Right. So let's go back to the case of ds, where now the classical solution must solve the equation that, you know, box is 0, the de Sitter box, okay? And then it's this type of phi. Okay. So we want, remember that there's a little bit of, in my conventions, I want the solution to behave like, so the general classical solution is going to be alpha 1 plus I k eta e to the minus I k eta plus beta 1 minus I k eta e to the plus I k eta. And here, for the harmonic oscillator, to get the right answer, you picked this solution by regularity. So by regularity, you're going to get the phi classical is beta. So now we want, remember that the argument of the wave function is a C number, phi of x. So what you do is you take your phi of x and you talk about its Fourier modes. Okay, so there's some C number, you decompose it into Fourier modes, there's going to be some phi k. And the idea is that the wave function, because it's a free field, is going to be Gaussian. It's going to be e to the minus integral over d3k, phi minus k, times something. And our job is to compute this something. Okay? It's just a Gaussian. Just like here, it was f squared. It will be just for every Fourier mode, there's going to be some Gaussian, and in some sense, the whole work is to compute the on-shell action to find what multiplies this phi squared. Here, it's important to put some cutoff. Let's choose some eta star. Okay, so I want at eta star, the Fourier mode, to have amplitude phi k. So then what's the solution? So I want phi classical at eta star to be equal to phi k. Okay, so that fixes beta. So such a way that what is phi classical? 1 minus. So let's plug this equation here, and we get beta. Then you tell me what beta is. Phi k is there, good. That's it. You're not done? Okay. That's the answer. Okay. So that's it. So now you plug this in, and you're going to get a little surprise here. Okay? You're going to get a little surprise that the answer, well, you know, the 2-point function from Born's rule is just the inverse of the real part by Gaussian integration, right? So the 2-point function of phi, the thing we computed, is just minus 1 over 2 times the real part of this, let me call this thing psi 2, okay? The wave function coefficient at quadratic order. Is it clear? You do mod squared, so you pick the real parts of this. 2, because you add psi 2 plus psi 2 star, and then you do Gaussian integration, it appears in the denominator, using Born's rule, Max Born. Okay? Everyone watched Grease here, the movie? You don't know Grease, too young, huh? John Travolta, Olivia Newton-John. You know why I'm telling you this? She was the granddaughter of Max Born. So, and yeah. is related to Max Born. Anyway, trivia of the day. So going back here, if you plug this in here, so we know what the answer is h squared over 2k cubed. So it shouldn't surprise you that this has a k cubed over h squared. So this is the right answer. But it has another term, and that's the reason why I needed eta star. And the other term looks something like this, and I invite you to compute it. Maybe I have in my cheat. Yes. Okay, let me give you the full answer, the correct answer. Then you can compute it. It's very simple. It's 1 over 2h squared I k squared over eta star minus k cubed plus stuff that vanishes as eta star goes to 0. But there's a term that blows up as eta star goes to 0. So this is a big oscillatory phase, which is related to this wave function is very WKB-ish. It has a big phase. The field classicalizes, okay? So that's what this is telling you. But this is the holographic network, right? So what does that remind you of? That should scream of something that as holographers you're all very much familiar with. So look at this term here. Remember, what's the analytic continuation to Euclidean ADS? You send eta to IZ and H to I R ADS inverse. So this phase becomes pretty real. It seems that the partition function of the CFT with this scalar boundary condition, with this Dirichlet boundary condition, is blowing up. But don't worry, my friend, everything is good because No. In ADS, there's no Born rule. This is just the on-shell partition function. You're just computing the on-shell action, right? This is you don't count. So you probably know the answers. The students. Nope. Okay, so now you can say. It's holographic renormalization. Yes. Thank you. Why? So this is local, it's k squared. So this, if you Fourier transform back to position space, is a local operator. It's just d phi squared of the boundary. So you can just renormalize and remove this. So this IR divergence of the path integral, you can remove with a local counter term. But in the Sitter space, it has some interesting interpretations, a big WKB phase. So that's so the ADS story of holographic renormalization is mapped onto this big growth of the phase factor. Yeah, it doesn't continue. So when you take mod squared, this drops. Yeah. You need to remove it with a local counter term.
Okay.
Yeah. Okay. So you see the story is different. You take complex saddles, but then in the end you land in the same place. So how does the story work for I stop at 11, is that true? Not 11:30? Just checking. So how does the story work for the interactions? So now the point is that you need to solve the equations of motion with these interesting boundary conditions. So you know that to solve classical equations of motion, we use diagrams again. We use propagators and whatnot. But the types of propagators will change because of this boundary condition. And now there's no double time. So now the figure, there's only one time. And what you do is the type of propagator changes a little bit. So at 3 points, there's only one type of propagator. And this, from as holographers you know and love, it's called the bulk to boundary propagator. So this wave function computation is very much similar to how would you compute the partition function in ADS. Okay? So you have bulk to boundary propagators, and you have, at 4 points, there's only one diagram to compute there instead of 4. But here you have the bulk to bulk propagator. So this is not the Feynman. So this is very much like the Whiteman function. It's very similar. It's essentially the Whiteman function. Okay, because the time ordering is manifest. This is not the Feynman propagator. And the reason is because the bulk-to-bulk propagator, you already solved the Dirichlet problem, right? So here, to compute the wave function, you specify some data, some boundary waves, some phi k, and these propagators already put this data for you. So this propagator better have no support. So this guy has an additional, so bulk-to-bulk is like Feynman plus some homogeneous piece, and the homogeneous piece enforces that as eta 1, let me call this eta 1, eta 2, and this is eta star. Either eta 1 or eta 2 go to eta star, the propagator vanishes. Okay, so that's the boundary condition. Okay. So let me show you what the propagators are if you were to do the wave function of flat space. Forget about the sitter. Let's just take flat space, take a fixed time slice. Say you want to make a measurement at time equals 0. You put some field configuration and you want to compute the wave function of that configuration. So and we do a scalar field. So the bulk to boundary propagator let me call it K. I think that's standard notation. It depends on the wave number and eta star is going to be e to the I k eta minus eta star. Okay, and I put the coefficient of the propagator to be 1 because it's going to multiply the field. So I mean, you could have put phi k here, or you could define the coefficient of the wave function to be what multiplies phi k, in which case this normalization here is 1. Okay? So as eta goes to eta star, I want this to be 1. And then bulk to bulk. Then the propagator looks like this. It will look very similar to what you know from QFT. 1 over, sorry, this is the frequency, right? We're in flat space, so as usual, omega squared is k squared plus m squared. Okay, so it's the frequency, so there's going to be 1 over 2 omega, theta function. This is what you learned from quantum field theory 101, your first course on quantum field theory, e to the minus I omega eta 1 minus eta 2, plus the other time ordering, eta 2 with eta 1, minus, okay, so this closes, minus 1 over 2 omega, e to the I omega eta 1 plus eta 2. Let me put, I don't remember the answer, so let me put eta star equals 0, okay? So I'm cheating, sorry. I just don't remember by heart. I mean, it's a trivial thing to recover the eta star dependence. This. So this breaks time translation symmetry, okay? So this is eta time translation invariant. This is not, because you picked a surface, eta star equals 0, to do your measurement. So here you do, so this term is peculiar. So this is the Feynman propagator, and this enforces the boundary condition, okay? So strictly speaking, there are 3 diagrams because there's one time ordering, the other time ordering, and the boundary condition. So there's some sort of conservation of difficulty. It's not that, there's only one diagram, so I'd rather do the wave function than in. So the wave function just packages all the terms of the in propagator into one propagator. Okay? So that's it. So you have to do this time integral. So when we are back from our break, no, then there's Geo, then nothing. Then after lunch, I will tell you a little bit more, and I'll show you what the bootstrap equations look like in the sitter space. So I think it's a good point to stop here. I'll take questions.
Okay, questions? I have a question, so I'll give you time to think. We can further discuss this in lunch if you want, but I have already done these computations sometimes, so it does look like you got a complex saddle because you chose complex boundary conditions.
That's right. But this is standard because you're trying to select the vacuum of the interaction theory, right? So
no, I agree, but I would like to discuss further with you. I seem that there is a rabbit inside the hat. Like there is we've done something magical here. Let's discuss this later. But
okay, sounds good.
Someone else? Maxi. Never fail. Thank you, Maxi.
Okay. Can you remark the different questions that we answer from the 2 formalists, formalists and...
So in is really about the physical observer. So you should think of it as the wave function is the amplitude and the in is the cross-section. So in is really the thing that you would feed to your cosmologist friend, say time evolve it and let's see. While wave function is very much similar to what you would compute in ADS, and it looks like a scattering amplitude, is more connected to also flat space amplitudes and so on. So that's the reason why. So some properties of the wave function are more transparent than the properties of the in correlator, but they're essentially equivalent, okay? So if you were to compute in correlators of the fields and the conjugate momenta of the fields, you have the exact same information as the wave function. Just one is more convenient than the other. So the wave for certain things. So the wave function coefficients, they have the same kinematic properties of CFT correlators. That's why people talk about DS-CFT. So it's useful to leverage CFT kinematics to learn about these guys. The in correlators, not so much. So it's more a matter of convenience, but they're equivalent.
Okay, thanks.
Okay, someone else? Okay, we thank Guy again.